In today's lesson, we are going to be looking at exponential decay. So this is going to be very similar to our previous lesson on exponential growth, except we're kind of going in the opposite direction. We are going to be decreasing or decaying instead of growing. Now, in general, right, the formula looks pretty much identical to the exponential growth formula, right? Y equals A times B to the power of X. Our X variable is our exponent. We have an initial amount and we have another factor. However, it is not a growth factor. Right? Instead of a growth factor, it is a decay factor. So it'll be a decay factor, and B will be not greater than 1, it will be less than 1. Right? So that is the key difference between the exponential decay and the exponential growth. It's going to look almost identical, except our decay factor is going to be less than 1 because we are going to be decreasing. Right? Y is still going to be our future amount, and X is still going to be the number of times A has decreased. Right? To calculate X, we'll still have a specific formula, right, or a small calculation to do, the total time divided by the time of one decay period. Right, so very similar to what we've done with growth, except in this case, we are decreasing. So let's look at a quick example. Right, so nuclear power plants use uranium-239 as a power source, and uranium-239 has a half-life of 2 years. So what that means is that every 2 years, the amount of uranium there is, it will decrease in half, or it'll be half remaining. So it'll be half of a certain amount, then half of that after 2 years, then half of that amount after 2 years, and so on. So we want to complete the example or the chart for an amount of 1,000 milligram sample, and we're going to be looking at 10 years. Right? So in year 0 or 0 half-life periods, we're starting with our initial amount. After 1 half-life period, there is 500 remaining, or 500 milligrams. After another half-life period, there would be 250 because it's half of the 500. After 3 half-life periods, there would be, or 6 years, there would be 125. After 4 half-life periods, there would be 62.5. And after 5 half-life periods, there would be 31.25. We can graph this relation as well. Right, so we can see that it starts at 0, it starts at 1,000, at 1, it's 500, at 2, it's 250, at 3, it's 125, at 4, it's 62, and at 5, it's about 31. So you can see it's just the opposite of the growth, it's decreasing. So we can see that little bit of difference. Oops, so I kind of messed it up. I was going off of half-life periods, not years. So year 2, it's 500. Year 4, it's 250. Year 6, it's 125. Year 8, it's 62. And year 10 is 31. My mistake, looking at the growth, the decay periods, not the actual years. So it looks like it is going to touch 0 or reach 0, but if you think about it, right, if I'm taking half of something continuously, it's never ever going to get to quite 0, right? Because I take half of a half, I get down to a quarter, and I keep on taking a half, and so on. It doesn't quite all get down there, right? So we could say, oops. Put a small note, doesn't reach 0. Right, so we just want to make sure that it doesn't reach 0, right? Even though it does look like that, it will still be, if we were to zoom in, it would look like there would be a gap between the x-axis or 0 and our line. So it's going to get very, very, very close, but it's never going to quite reach 0. So we want to write an equation to model this growth, right? So we talked about the general equation already, right? And because it's a half-life, that means our decay factor is 1/2, right? Because it's decreasing by a factor of a half. So in our equation, y equals ab to the power of x. In this case, it's going to be y equals 1,000 times our factor, which is 1/2, to the power of x. And we could argue that x should be divided by 2 because we take the number of years and divide it by 2. Because it's 2 years, or the half-life is 2 years. Now, how much remains after 25 years? So we're going to basically take our formula we just determined, 1,000 times 1/2 to the power of x over 2. So in this case, 1,000 times 1/2 to the power of 25 divided by 2. Or y equals 1,000 times 1/2 to the power of 12.5. Because you would argue there are 12.5 growth periods or half-life periods, or sorry, decay periods, not growth, in 25 years. This just becomes a calculation. We go through and we solve. We get 0.1726 milligrams. So after 25 years, there would be 0.1726 milligrams of uranium-239. Right, so even after 25 years, it's still not going to disappear fully. And that is the danger of having nuclear materials, that it doesn't quite disappear. So looking at another example, so plutonium-239, so another radioactive material, has a half-life of 24 years. We want to find the amount of a 500 milligram sample left after 35 years. So some key things to highlight. Half-life of 24 years. So half-life tells us the factor. 24 tells us the length or the time of one growth period. So we're going to need that to calculate our x or our exponent. 500 or 50 milligram sample, and we're looking at over 35 years. So our A is going to be 50, our B is going to be 1/2, and our x is going to be 24/35. So for our equation, y equals 50 times 1/2 to the power of 24/35. We would actually determine what that fraction is. We could use a decimal, or if your calculator is strong enough, you could leave it as a fraction in the exponent. So we calculate this, just plug it into our calculator. We would get 18.2 milligrams of P239, or else do therefore. So therefore, there will be 18.2 milligrams of P239 left after 35 years. So again, after 35 years, there's still about almost close to 20 milligrams of P239 left. Right. So again, that's quite a long time to have stuff remaining. Similar to if the exponential decay is given as a percent, right? If we're told that it's decreasing or decaying by a certain percent, or there's a certain percent remaining every year, right? We can use a similar formula, y equals a1 minus r to the power of x. So very similar to the other formula for exponential growth. The only difference is instead of adding an r, our rate, we're subtracting our rate, which makes sense because it is a decay, not a growth. A is still our initial amount or population. R is our decay rate as a decimal. Y is the future amount or value, and X is the number of times A has decreased. Right, so again, everything represents the same thing. The only key difference is that now it's a decay rate instead of a growth rate. So just how the question is going to be worded. So for example, You buy a new car for $24,000. The value of the car decreases by 16% every year. How much will a car be worth after 8 years? So our initial value, right, we'll go through highlight 24,000. We see it decreases by 16%, and we're going to be looking for the worth after 8 years. Our initial value is 24,000. Our R is 0.16 or 16% as a decimal. Our X value is just going to be 8. We don't have to do any calculations because it's decreasing or decaying by 16% every year. Right? So because it's every year, we don't have to do any kind of extra calculations. I'm going to plug this all into my formula. Y equals A 1 minus R to the power of X. So Y equals 24,000 times 1 minus 0.16 to the power of 8. Y equals 24,000 times 0.84 to the power of 8. When we calculate this, we get a value of 5,949.02. Therefore, after 8 years, it is worth $5,949.02. So not a lot of worth after 8 years, right? But again, that's cars, right? They lose value very quickly as soon as they're used. So after 8 years, this $24,000 car is going to be worth about $6,000. So basically almost a quarter of its original value. So we can also look at this not just in value, but we could also look at it in kind of amount remaining, similar to the half-life, except we're dealing with medicine. So an adult takes 400 milligrams of Advil. Each hour, the amount of Advil in the adult system decreases by about 29%. How much Advil is left after 4 hours? So again, we're going to go through highlights. So 400 milligrams is what we take initially. Decreases by about 29%, so that decrease each hour. Right? So that kind of gives us the growth period, and we want to figure out how much is left after 4 hours. So in this case, our A value is 400. Our R, or our decay rate, is 0.29. And it says decrease, so that's how we know it's decay. And our X value is going to be 4. Because it decreases each hour, right? That's the time of a decay period. We don't have to do any fancy calculations because we're looking at 4 hours as well. So Y equals 400, or A, times 1 minus R, or 1 minus 0.29 to the power of 4. Simplify this bracket, 0.71 to the power of 4. If you want to do that calculation beforehand, you can do that as well because it's going to be just subtracted from 1, nothing fancy. And in the end, when we calculate, we should get 101.65 milligrams. So therefore, 101.65 milligrams of Advil left after 4 hours. So similar to the exponential growth, we might have to find how much or how long it's going to take to decay to a certain amount. So this setup's going to be similar. We're going to use logarithms in the same way to help us move our x exponent down. So in this case, let's go through and kind of highlight half-life of about 2 years. If you start with a 1,000 milligram sample, how long will it take to decay to 10 milligrams? So we know that our Y value is going to equal 10, or our future value. We know our A value is 1,000. We know our B value is going to be 1/2 because it's a half-life, so we're not given a percent, we're given a factor. And we know that X is going to be x over 2 because it's a half-life of 2 years. So I'm going to take all this information and plug it in. So y equals, we're going to start with, I'll start with the initial one without plugging in that 10. So y equals 1,000 times 1/2 to the power of x over 2. I would now plug in that 10 for that y value. So 10 equals 1,000 times 1 over 2 to the power of x divided by 2. I'm going to show all the steps, right? As you become more comfortable, you might omit showing these steps. I'm going to divide both sides by 1,000 first. One side will cancel out. We're left with 0.01 is equal to 1/2 to the power of x over 2. Here is where I need to get rid of, or I need to bring this exponent down. In order to do that, similar to what we did with exponential growth, we are going to take the logarithm of both sides. That will allow me to move this exponent down in front. So I would end up with log 0.01 is equal to x over 2 times log of 1/2. Now log of 1/2 or log of any number is just a number. Right? So I can treat log 1/2 as a number. I'm going to divide both sides by log 1/2. One side will cancel out, and I end up with a value on the one side, or 6.69 is equal to x over 2. Now I just have to solve for x, so I'm going to multiply both sides by 2. One side cancels out, and I'm left with 13.3 equals x. So therefore, it will take 13.3 years to decay to 10 milligrams. And so again, similar idea, similar setup to when we had to solve for x with our exponential growth. Just in this case, we just had a different factor or a different b value, but the steps were the same. Lastly, we're just going to go through and just kind of do some calculations just with some exponents, just kind of revisit our power laws, just to make sure we're familiar with them, dealing with exponents, dealing with a variable in the exponent. We should know our power laws. So x to the power of -2 times x to the power of -3 times x to the power of 4. Right? This would be the same as adding -2 plus -3 or -3 plus 4. We add our exponents, we get x to the power of -1. But to keep it as a positive exponent, it's 1 over x. We flip our base. For b, a squared divided by, or a squared times b to the power of -3 divided by a to the power of -1 times b squared. I'm going to focus on the individual components first. I'm going to treat, or I'm going to simplify using the power rules for dividing powers, which is subtraction, and then I'll worry about the positive and we're getting positive exponents later. So a squared divided by a to the power of -1, we subtract, that becomes a to the power of 2 minus -3, or a to the power of 3. For b, b to the power of -3 minus 2 is b to the power of -5. And now to get a positive exponent, I bring my b down, so it becomes a cubed over b to the power of 5. For c, I'm going to multiply, or I'm going to carry this exponent all the way through to each part. So that means it'll be 2 to the power of -3. For u, power to a power, we multiply, so u to the power of -9 and v to the power of 6. I'm going to bring my negative exponents down, so the v to the power of 6 will stay up, but on the bottom we'll have 2 to the power of 3 and u to the power of 9. I can then simplify this because 2 to the power of 3 is 8. So this simplifies to v to the power of 6 divided by 8u to the power of 9. For d, 1/2 to the power of -1. Right, when we have a negative exponent, we flip our base, so this becomes 2/1 to the power of +1, or just 2 to the power of 1, or just 2. And for e, similar idea. I'm going to flip my base, so this is going to become -8/27. I don't change the sign in the base, I just flip it, and it becomes a +2. This exponent 2 applies to both parts, so this works out to 64/729, and because one of them was negative, a negative times a negative is a positive. So very similar lesson to exponential growth, just in this case we're looking at things decreasing instead of increasing. Steps are going to be almost identical to calculating or solving for different components. The only thing we have to be considerate of is, one, that the b value should be less than 1 because we're decreasing, and when we're dealing with a growth decay as a percent, we should be minusing it from 1 instead of adding it. Other than that, the steps are the same, types of calculations are the same. You're just going to have a different decay factor because now we're decreasing and not increasing.